All right, guys, no picture of my lovely face today. I know that's going to make you all very, very sad, but I do want to go through and talk to you about different star properties and the HR diagram. So let's go ahead and get started. Um, the first thing we need to do is define what we consider our solar neighborhood. So distances can be measured using what we call parallax. So this is how we determine how how close things are to us. So if you put your thumb in front of your face and you close your left eye and then you close your right eye, so do this right now, and close your left eye again and then close your right eye. What do you notice about what the background appears to be doing? Hopefully you notice that it seems like the background is moving, but it's not really. So when you do that, you're looking at parallax, and we are able to use math, and I'm not going to make you do it, but you're able to use math to be able to determine how far something is away from you based on how much that thumb appears to move. And that's actually what surveyors do. So if you're driving down the highway and you see them looking through that little camera thing and you drive over the little bumpy thing, that's what they're doing, is they're trying to determine distances so they can very accurately determine where they're going to go with what they're doing with the road. So our next nearest star is called Bernard star, and it has what we call the largest proper motion of any star. So proper motion is the actual motion that you see in the sky, right? So the stars all appear on that celestial sphere, remember? They all look like they're tacked at the exact same distance from each other, but they're not necessarily. And so Bernard star is one that doesn't stay put on the celestial sphere. It doesn't move anywhere near as much as a planet does, but it does move back and forth a little bit. So we were able to use parallax to determine its distance from the sun. So here is Bernard's star, let's say in 1980, and here it is in 2002. So you can see it actually moved over 22 years. Now, the nearest star to us is about 4 light years away, and it's in the Alpha Centauri complex, and it's actually Proxima Centauri is the one that's closest. And to give you an idea of how close that one is, imagine that our sun is a marble. Then the Earth would be about a grain of sand about a half mile away if we were doing this to scale. Our nearest star would be another marble 630 million light years away. So that would be from Haymarket to Myrtle Beach, or I'm sorry, from Haymarket to Jacksonville, Florida. That's how far away that would be. And that's our nearest star. And so basically everything between us and Alpha Centauri is completely empty. So, distance, we talk about light years, and a lot of us want to think light years as a time because it sounds like a time, but it's actually a distance. So it's the distance that light travels in a year, and it travels at 186,000 miles per second. So that's a total of 5.8 trillion miles. So if you were to take $590 million and multiply that by 1,000, that's how fast it's going. So it's going really, really, really fast. Then we break that down into another section called parsecs, and a parsec is 3.26 light years. And remember, an AU is the distance of the sun to the earth, right? So a parsec is 206,000 AU, little bit farther away than Earth. All right, so now let's take a look at this. If you look at these, and I know you guys are saying, this is a trick question. I know that it's a trick question, and it probably is, or it's not meant to be. But if you look at these, and I were to ask you which is the closest star, so in your head, take a look. Which one do you think is the closest, and which one do you think is the farthest away? Okay, most people are going to say this Alcyone is the closest, right? Because it's the brightest, and then Atlas, and then Pleione. That's how most people would take a look at that. However, if you look at their actual distances, this first one is 440 light years away. The brightest one is 440 light years away. The next dimmest one is 435 light years away, and then the dimmest one is 492 light years away. So even though they're brighter, they're not necessarily that much farther away from us. And we call that luminosity, or absolute brightness. And that's a measure of the total power that's radiated by a star. So the total amount of energy, it's basically like a light bulb. It's the number of watts coming out of that light bulb. We know a 100-watt light bulb is brighter than a 60-watt light bulb. It's the same thing with stars. So apparent brightness, again, a good definition, or I'm sorry, apparent brightness is different. Apparent brightness is how bright a star appears to be when it's viewed from Earth. And it depends both on absolute brightness and the distance of the star from Earth. So a really good example that I like to use, and it's fun in the classroom because I always get a flashlight out and I shine it in somebody's eyes and I say, imagine that this light is, right here in front of you, but there's a truck behind me with high beams. Which one is going to appear brighter? So the truck that's 50 yards away with high beams isn't going to appear very bright compared to that flashlight in your eyes. But obviously the flashlight in your eyes isn't giving off as much light, right? And that's because of its apparent brightness. So two stars that are equally bright might be a little bit closer. So the bright star might be closer and the dimmer star might just be farther away, even though the brighter one, the one with a higher luminosity, is closer or farther away. Sorry, now I'm confusing myself. Now, the color of a star is related to its temperature, and in space, red is cool and blue is hot. And I know when you watch the video, Mr. Hanna gave a really good example where on Earth, if you go to wash your hands, the red in your house, or especially like even in the bathroom, oh no, not in the bathrooms here, but in the bathrooms when you go out to eat or whatever, the red is the hot one and the blue is the cold one, but it's backwards in space. Red is actually relatively cool and blue is actually really, really hot. So we have to keep that in mind. So we break those colors down into 7 categories of what we call spectral classes, and they correspond to different temperatures. So the in order, they're O, B, A, F, G, K, M, right? Like you're going to memorize that right away, right? So just remember, O, be a fine girl, kiss me. It's a little outdated. It could be, oh, be a fine guy, kiss me, right? But either one, and make sure you get permission before you do it, right? We need to make sure we do that. But anyways, make sure that you remember O, B, A, F, G, K, M. And we'll put that into an HR diagram here in a second. So, and on your graphic, you'll need to include these as well. The approximate surface temperature, as you can see, it matches. So the O is the highest at 30,000 and the M is the lowest at 3,000. And this gives you an idea of the different elements that are inside, and then this gives you examples of those stars. When you do your Gizmos lab, you're going to be looking at this in detail. And we talked about stellar spectra, and what we didn't talk about is how the stellar spectra can also help us determine what the temperature of the star, because really, really hot stars are going to be burning a lot of hydrogen into helium, and stars that are, well, I'm sorry, backwards. Stars at the beginning of their life are doing hydrogen into helium, and they're not necessarily as hot when they're doing that. But when they're burning heavier elements like carbon into iron, they need to have really, really hot temperatures in order to do that. So those stars get a lot hotter. The stellar spectra tells us about this temperature by looking at its chemical composition. For most stars, it can't be imaged directly, right? We can't measure it perfectly, but the size can be calculated by knowing the luminosity and the temperature. So let's look at some stellar sizes. The giant stars have radii that are between 10 and 100 times the sun's. Dwarf stars are equal to or less than the sun, so our sun is considered a yellow dwarf. And supergiant stars have radii more than 100 times the sun's. So what about stars that are a little bit bigger than the sun or up to 10 times the size of the sun? They're not considered giant stars, but gosh darn it, they are pretty big. So now we have the HR diagram, and the HR diagram is a graph, and it's actually an easy graph. They have luminosity on the y-axis and surface temperature on the x-axis. And notice you have the spectral classes at the bottom here. Oh, be a fine guy, kiss me, right? So they're down here at the bottom, and you can also just kind of put them in here for you. So that means all these stars are going to be blue, all these stars are going to be white, and all these stars are going to be red. And this is telling you, one is how bright the sun is, okay? And the sun is about, on its surface, it's about 6,000 Kelvin. So you look at that, and so sure enough, at luminosity 1 and 6,000 Kelvin, you have the sun. So these stars are going to be a little bit brighter. So let's take a look at Rigel. What's Rigel's surface temperature? Okay, hopefully you said it's probably about 12,000, right? What color is it going to be? It's going to be blue-white, right? And what's its luminosity? It's going to be over 10,000. Now, hopefully you noticed while you were trying to read that graph that the bottom is a little bit weird. The same distance between 3,000 and 6,000 is between 6,000 and 10,000. And the same distance between 6,000 and 10,000 is 10,000 to 30,000. So you just have to pay attention to that part of the graph while you're actually graphing things in your gizmos. Now, when you plot a bunch of stars on the HR diagram, this pattern seems to emerge, and this pattern is going from the upper left-hand corner to the lower right-hand corner, and it's this kind of curvy line, right? And so we call that the main sequence. And you learned when we were talking about the stellar life cycle that the main sequence is where most stars spend most of their lives. Well, all stars spend most of their lives there. So they, again, in the upper left-hand corner to the lower right-hand corner. So this is your giant stars, and this is your dwarf stars. This is plotting the 100 brightest stars, and this looks a little bit different. So you notice the brightest stars are above the or above the main sequence, and that's because they are over their surface temperature is relatively cool, but they're over 10,000 or 100 times more luminous than the sun. So they're a lot brighter than the sun. So these are your giants. This is where stars go when they're about to die, right? So they're on the main sequence, and then after a period of time, they start appearing in the upper right-hand corner. This is, if you were to plot most of the stars in the sky, so this is 90% of the stars, you can see that there's quite a bit of pattern. You can see this main sequence is where most of these stars are, and then you have stars tailing off into the red giant region. And so that's everything you need to know about the HR diagram and stellar properties. Hopefully you don't have any questions, but if you do, you know that I'm around there for you. There's also some really good videos that you can watch, and there's a guy with an Australian accent giving another lecture, and it's about the HR diagram. If you're doing your lesson on the HR diagram, I highly recommend you watch him. He's really, really good. I think his lecture is better than mine, but you guys are used to me, which is why I went ahead and put mine here too. So again, any questions, you know I'm around, and